Okay, now that we have vectors, we can do all the other tensor stuff. And so this is the same. So dual vectors. Those are maps, linear maps. From vectors to the reals. And we're going to introduce a nice basis. So we have our coordinate basis vectors. That's d by dx mu. I should call this a coordinate basis. You don't have to use coordinate bases. You can use any basis you want, but you pretty much almost always do use a coordinate basis. It's the most convenient, except for some specialized calculations that we won't really do in this class. And remember, we got a basis of one forms from the basis of vectors by the equation theta hat upper mu, our basis labeled by mu for one forms, acting on E hat lower nu is equal to delta mu nu. And we're going to do the same thing here. But now we have a new notation for E hat nu. That's just d by dx nu. That's our abstract vector. And these things here, we actually already have a name for them. They're actually the gradients of the coordinates. So if you think about what the gradient vector does, it answers questions like, you give me a vector and I'll tell you how fast the function is changing in the direction represented by your vector. So for example, if we do the gradient of x, it answers how fast is some function you've given me changing in the x direction. And if given in whatever direction you plug in, and if I plug in the direction y, well, x doesn't change at all in the y direction. Okay. So that's why that's 0. And how fast does x change in the x direction? Well, unit speed, right? So if you like, just imagine I'm naming theta hat dx mu, but it really is the gradient of the coordinate functions. Okay? So we have this is our coordinate basis for vectors, and this is our coordinate basis for dual vectors.
If the dx, the thing in the brackets, should that be d over dx?
Yep. Thank you. I always say these things triumphantly as if I've written the right thing. I assure you in my head it was right. Thank you. So that's really it. I don't have anything to say more about dual vectors. We went through all that in the context of special relativity. This is identical. What about tensors? Well, same things, right? Multilinear maps. Etc. Definition is identical. The basis we get is just gotten by tensoring together all these different coordinate bases. So for example, I don't want to write out n upper and m lower indices or something, but I could just do t mu nu alpha or something. That's an example. So the abstract tensor t is its components. And now I need d by dx mu if you like, tensor product. We're almost always not going to write that. D by dx nu, tensor product dx alpha. So this is our abstract tensor. These are our coordinate basis components. And these are our abstract coordinate basis elements. Okay, so again, a tensor is, if you like, just something with some upstairs and downstairs indices following all the rules, but this is the formal expression as an abstract mathematical object according to the definitions we've given. Now, one thing that will change is the transformation law. Yep?
What's the little alpha in the equation that you wrote?
Just a lowered index. I'm just doing a tensor with, yeah. So we will need to think about the tensor transformation law, much as we talked about in special relativity, how vectors transformed one way and one forms another way. How do you get their components in a new Lorentz frame? Now we have this more general notion of any coordinate chart on the manifold. And we have these overlap regions where two coordinate systems are valid. And we want to know how to write a tensor in one coordinate system in the other coordinate system, how to find its components in the new coordinate basis associated with the other coordinate system. So here's where we get a lot of mileage out of the definition we used for vector. So recall that we had a vector v would always be written v mu times the abstract vector d by dx mu. And from here, we do the same game. We say, well, we ought to be able to do that in some other coordinate basis associated with some other coordinate system, x mu prime. So now we just have, in general, some function x mu prime of x nu. It's not a Lorentz transformation. It's just any, and remember, these are the overlap maps from Rn to Rn for the two charts, and so these have to be invertible functions. So we'll just say smooth. Any smooth function from Rn to Rn. And we know how to relate partial derivatives in one coordinate system to another. That's the chain rule from calculus. So we have d by dx mu prime has to equal dx mu dx mu prime d by dx mu. This is just the chain rule for partial derivatives. In a slick notation where I can't possibly mess it up because I get to line up the primed indices downstairs and make sure there's one up, one down for the unprimed indices. So we put this into our equation. I may end up getting the inverse transformation depending on how I wrote this, but let's plug this in here.
Would our function x mu prime not be a function of x mu instead of x nu?
I don't know, they're just labels. I mean, it's just some map. I could have said mu, yeah. Here I'm saying mu. So we put these in. And then this one here becomes mu prime, v mu prime dx mu prime d by dx mu from that one. But that had to equal this, equals v mu d by dx mu. And then these partial derivatives, the basis vectors, they're a basis, so they're linearly independent. So we can peel them off. And this implies that v mu, so I did get the inverse transformation, doesn't matter, we can interchange primes and unprimes. V mu is v mu prime dx mu dx mu prime. This is the transformation law for the components of a vector. If you have the components of a vector in one coordinate basis, v mu prime, associated with one coordinate system, x mu prime, you get the components in another coordinate system by this, looks kind of like a matrix multiplication. And, well, it is a matrix multiplication. Does anyone recognize what matrix this is? Jacobian. Jacobian matrix, exactly. Okay, so we know, because we assumed all those overlap maps were smooth, we know this thing exists and is invertible. So the inverse of it, the nice thing about this notation is the inverse of this matrix, so exists by assumption, and it's written dx mu prime dx mu. That's a theorem of calculus, if you like, that the inverse Jacobian matrix is the Jacobian of the inverse transformation. And the notation just makes it inevitable. Right? If I wanted this equation to hold with the primes and unprimed interchanged, this is what I'd end up with, and it has to be the inverse for everything to hold together. So the notation really prevents screw-ups. Questions?
I have a quick question about the coordinate basis.
Yeah.
So both the dual space and the tangent space, right, like they are just inheriting a coordinate system from the base manifold. So
They're inheriting a basis from the coordinate system of the manifold.
okay.
And the, space of tensors of rank 3, 2 is some, I don't know, some 3 copies of the space and 2 copies of the dual space. I think they call it direct product for the spaces, not tensor product, although physicists use the same. And so that one gets a basis from the coordinate bases tensored together, like these ones here. Well, the bundle notion has to do with the fact that there's a separate tangent space at every point on the manifold. And so the structure of, if you want to talk about vector fields on the manifold, strictly speaking, they live in the tangent bundle, which is just the set of all the tangent spaces at each point, which has to be a bundle because it might only locally be a product. It might not globally be a product. So the manifold together with the tangent spaces is the tangent bundle.
Do you ever have to use non-coordinate bases in GR, or is that like it's just too convenient?
There are some calculations which are a little easier with non-coordinate bases. The most important is something called the Newman-Penrose formalism, where you have actually 2 null vectors and 2 complex null vectors, and you use those as your basis.
Okay.
That really, I've never seen anyone profitably use just ordinary orthonormal frames. I think they might save you some work when you do long calculations, but nowadays you do this on a computer anyway, so it just doesn't come up too much. I will give a homework problem maybe this week, I haven't uploaded it yet, on exploring the difference between vector calculus and curvilinear coordinates as you did it using orthonormal bases in E&M, and the way you would do that using coordinate bases in GR. They are different. So the formulas for things like div, grad, and curl look different in coordinate bases from orthonormal bases. Other questions? So that was vectors, but you can guess what's going to happen. One forms will just transform the opposite way. Well, since I did the prime on the right, let's keep that. So we'll have omega mu prime, and then you just follow the notation. It's some kind of Jacobian matrix. And well, there's a prime down here, so we better put one up here. And then this unprimed mu in the bottom of the derivative counts as a lowered index, and it matches. And similarly for some other tensor, T mu alpha beta, just making it up, you'll have the same thing over here with primes, and then you just need 3 Jacobian matrices. So I'll ceremoniously write all of them out without any coordinates on them. And then I'll just start filling in the coordinates. So I got an upstairs mu prime. I better put one down. And then here there'll be a mu to match that mu on the left. I've got a downstairs alpha prime, so I better put one up. And there'll be an alpha down to match the alpha on the left. And I've got a downstairs beta prime, so I better put one up. And put the beta down to match the beta on the left.